Welcome viewers to the session on Galerkin weighted residual method in the course Finite Element Methods for Beginners. In previous session we have discussed about the Ritz method, that was one of the approximate method, and in this particular session we will be taking up weighted residual methods, the types of weighted residual methods, and then the application of Galerkin weighted residual methods for heat transfer problem. So let us begin our session. In weighted residual method, we discussed that if we represent our governing equation by some function f phi of x that is equal to 0 in domain omega, and it is satisfying the boundary conditions as g1 function of phi of x that is equal to 0 on boundary 1 and g2 on boundary 2. And we discussed that we assume a function for the field variable, and that function we can write for n terms as ai ni of x, and this ni is named as trial function. And for the Ritz method, if we substitute back this assumed function into this, we get f phi dash is the assumed solution for this particular problem. This will not be equal to 0, it will not exactly satisfy this governing equation, but we will get some residual error. And for Ritz method, we have to reduce this error function to 0. And what to do for that? We have to take integral of this function, that is xi to xj or x1 to xn or xi to xn, and dx, that should be equal to 0. So this is what our aim is in case of Ritz method, that is for the complete domain. If we want to write in terms of the domain, I can remove these for 1D and I can write a general term, that is omega. If it is 2D, then it will be a double integration. For 3D, it is triple integration form. So this is about the Ritz method that we have discussed in our previous class. So in case of weighted residual method, what we have, that is that this integration, the residual integration, should vanish with the help of some weighted function, and that weighted function is written as wix if it is for one independent variable, and again the residual is to be multiplied with this. So residual function is a1 a2 up to an dx, and this should be 0. Again, if it is omega here, it has to be omega here, and likewise here, if I am writing here omega, this should also be replaced with omega, so that it represents the domain integration. If it is 1D, then it is dx 2D, it is the double integration here, dx and dy, and similarly here. So in case of Ritz method, we directly integrate. We want that over the domain this residual should be 0, and in case of weighted residual, we multiply that residual with some weight function, and the integration of that particular expression that we get after multiplication of the weighted function with the residual, that has to be 0. So this is what is the difference between weighted residual method and the Ritz method. And there are 4 different types of weighted residual method. Number 1 is point collocation method. Second is the subdomain collocation, and third is the least square, and fourth is the Galerkin method. So we will not be discussing point collocations, subdomain collocation and list square in this particular lecture. We will only focus on the Galerkin method, and that too directly in context with the finite element method, and the application will be on FIN. And in case of Galerkin method, we assume that the trial function that is nix, this is used as weighted function that is wix. So what we do, we replace this wi with the trial function that we are assuming for evaluating this residual from here. So it means here whatever trial function we have used for the approximation of the field variable, same trial function will be using for the weight function. If we are using the same trial function, then it is a weighted Galerkin method. It means our equation for Galerkin method will be replaced by. So this is what basically we have the equation for Galerkin weighted residual method. And no doubt here we know that A1, A2 and so on are constants, and we have to find out the values of these constants from this equation. That is in general, but we will be directly writing down or using this weighted Galerkin method in case of FEM. So in case of Galerkin weighted residual method applied to FEM, each equation is to be applied on each node of the element. So that is why we can write down the Galerkin equation for all the elements, that is element number 1 to element number total number of element. Then we have to integrate. If we are assuming that it is two noded element, then we are considering it means this element, here we have I, here we have j, this is coordinate is xi and this coordinate is xj, and this is the eth element. And here I can write down nix multiplied by the residual, that is function of x, a1 and a2 for the linear element, multiplied by the differential. Here I can write down omega, or for 1D case I can write down dx. So this is what is the general equation for finite element method when we apply Galerkin method. So when for the second node we have element number 1 to ne, the other part will remain same, xi, xj, ni will be replaced with nj because this we are applying on the second node of first element. The residual will remain same, dx is equal to 0. So in short, we can write down as summary that we have function which is over a domain. So I can write down this function fx dx0, that is the governing equation over a domain. This is equal to 0, and I can represent this equation for infinite element form as I is equal to 1 to ne, or this e is equal to n is equal to 1 or to ne, and then omega e f of x dx is equal to 0. So this is what basically, and this we are applying when we use weighted residual method, Galerkin weighted residual method. We use this function for each and every node. So here phi I can represent like this, that is summation of I is equal to 1 to n. That is, what is n here? N is the number of node per element. So this I can write as ai ni x. So for 1D case 2 noded, I can write it like this: a1 n1x plus a2 n2x. For element number 1, or in general we can write it AI NIX plus AJ NJX for a general element with I and J node. Now it is very important to understand this concept that this phi in the FEM or phi in general is a field variable which has to satisfy the boundary conditions exactly. It means in case of FEM, phi represents the variation of field variable within the element. The field variable is varying when we move from one node to another node in case of 1D element. So this field variable in case of 2D it will be within the variation within the element, and 3D within the volume of the element, and so on so forth, and hence it must be assumed that it satisfies the nodal field variable. It means what? That what is the value of the field variable here? It is phi I and here it is phi j. So whatever function we assume, this function that we have assumed to represent our field variable, it should satisfy the nodal variable values. So when xi is when x is equal to xi, this value phi should be equal to phi I, and when x is equal to xj, this value of phi should be equal to phi j. And within the element it is given by this expression. We can find out what is that expression, and we can find out what is the value of phi for within the element. In FEM, we can find that the shape function, the trial function in FEM, they are called as shape function. The shape function for ith node is given by xj minus x divided by xj minus xi, and similarly nj x is equal to xi minus x minus xi rather. So it is given by x minus xi divided by xj minus xi. So we can also derive these as the form. We can also derive these expressions using our basic concept of linear interpolation function that we'll take up when we discuss the shape function separately in some other video. But presently we'll assume that these are the shape functions that we have to substitute here. So it means what? When x is equal to xi, when x is equal to xi, this ni will be equal to 1. So at x is equal to xi, nix is equal to 1. And when x is equal to xi, here for this case, when x is equal to xi, nj is equal to 0. It means what? When we talk about this node and we try to evaluate our interpolation function phi, our field variable phi, I get this as 1 and this as 0. And what does it mean? That phi in this case, so this condition will give me phi is equal to ai, and ai is nothing but we should get value of phi at node xi is equal to phi I. Similarly, we can write down the other conditions when x is equal to xj. In that case, nix is equal to 0 and njx is equal to 1. So what does it mean? It means that for when x is equal to xj, this is 1 and this is 0. It means I get phi is equal to aj. And what should I get otherwise? I should get the value of nodal variable at node j, that should be equal to phi j. What does it mean? That phi should be equal to aj and that should be equal to phi j. So now from here we can write that our nodal variable our field variable can be represented like this. ai is to be replaced with phi I nix plus phi j njx. So this is an important expression that we will be using a lot for any finite element formulation. Proceeding further to apply this Galerkin weighted residual technique to the field problem of heat transfer, that is the heat analysis of FEM weighted residual method. So let me introduce one or two more terms and then we'll proceed further. So coming back to the equation that we apply in case of weighted this Galerkin method, we can write for each and every element and each and every node, because we have to apply this Galerkin method on each and every node. So I can write for n number of element that if for e is equal to 0 and e, I have to sum for this, integrate from xi to xj I x r x phi I phi j. Now I am writing this phi I and phi j instead of ai and aj. This is for node I. And similarly I can write down for the jth node for all the elements. I have to sum for all the elements to integrate it xi to xj. The only difference is ni will be replaced with nj. So I can combine these two equations, both these two equations, to get the form as summation of I is equal to 1 to number of element. This is xi and xj. I can write this equation ni and nj in matrix form. So this I can write as ni x and jx, and this is to be multiplied by, this is common in both the cases, so it is r of x phi I and phi j dx is equal to 0. So if I assume that n is given by the column vector, row vector, this is nix and njx, and transpose of this will be, n transpose will be equal to what we have written here. So it is nix and njx. So it means we can write with these two simplification, we can write this phi for element ni phi I plus nj phi j. That is our basic interpolation function that we have started for approximating the field variable, and this I can write as n. This n is nothing but this n. It is matrix representation, and this phi. So this phi is also matrix representation. So it means this n here is nothing but this value, and this phi is given by phi I and phi j. So we'll be using the matrix notation to represent now. It means I can write, let us not write this. If we do not write this, then it is, we can write this phi e is equal to n phi. So we will be using this to represent phi e, where n is nothing but it is row vector of the shape functions and phi is the column vector of nodal variable. And we also be needing the differentiation of this shape functions. So dn by dx, when we solve this, we will be needing the differentiation of these. So I will write here dn by dt is equal to the differentiation of this with respect to x and differentiation of this with respect to x. So I can directly write down dni over dx, and second element of the row is dnj over dx. And similarly I can write down the transpose of this from this equation. The transpose dnt dx is equal to the column vector. We can write down dni over dx either from here or by differentiating this d and j over dx. So we'll be using these terms quite a lot in our coming sessions. So that is why we have introduced some terms before applying the Galerkin weighted residual method to any field problem. So now we can move to the application of this weighted residual method using Galerkin formulation for a FEM problem. So we'll introduce FEM problem first, and then we'll apply this Galerkin weighted residual method to solve this problem. So let us consider a pen type pen. The one end is insulated. The length of this pen be capital L, and if I take reference from this, it x is equal to 0 here and x is equal to L here. This is base temperature Tb, the ambient temperature is A, the K, A, P are heat conduction coefficient or thermal conductivity, area of cross section and perimeter of the pin at any section. The fins are used where we want to increase the heat transfer rate, and that we achieve by increasing the surface area, as we know. The governing equation for this pin for this fin we know from our basic knowledge of heat transfer that it is Ka dt by dx minus h time P, that is perimeter, T minus Ta ambient temperature. This is equal to 0 when x is greater than equal to 0 and less than equal to L. And this is subjected to some boundary conditions. So boundary condition in this case, you tell me what should be the boundary conditions for the fin. It is temperature T of the fin at x is equal to 0 is equal to Tb. So this is where x is equal to 0. So this represents x is equal to 0. And temperature here, this is insulated. It means that heat transfer at this particular end is 0. So we can write down this as dt over dx at x is equal to L. So that is equal to 0. So this is when x is equal to L. So here it represents x is equal to L as well. So both ways we can write dt by dx only x is equal to 0 is t is equal to tb at x is equal to 0. So this is at x is equal to L. So this is our problem. Now this problem I have to solve using Galerkin weighted residual method. So now I can apply Galerkin weighted residual method on the differential equation of the uh, fin. So what I will get, it is xi to xj and transpose d over dx ka dt by dx, and then it is minus hp t minus t ambient, and then this bracket dx is equal to 0. So this is what my equation will become, where I can write down nt is nothing but it is ni and nj, this discussed previously, and t is nothing but ni ti plus nj t tj. So I can write this t as ni tj nij, and then this ti and tj, or I can write this as n times tj. Oh sorry, this is not t here, so n time t, and these are the matrix notifications, and this t is the expression. So this t is nothing but this, and nt is nothing but this. So now we will first focus on the first part of this equation. This second part will take up later. So let us focus on the first part, how to simplify the first part. So it is xi xj and transpose, then it is d over dx k a dt over dx multiplied by dx. So this first part is to be solved using integration by part. So if I integrate this equation by part, I will get n transpose k a dt by dx and limit xi to xj, because this is the differentiation, so only this part will be left. So this is what basically we get, and limit is xi to xj minus integration of this, integration of xi to xj, differentiation of first, that is d and t by dx, and then integration of the second, that is ka dt by dx into dx. So this is how we can get this. So now this particular term is very interesting in this fin type of problem, where we have the one end insulated. So this term where it is the heat transfer within the element, then at each node, when we consider each node during assembly, the heat transfer from here to here and here to here, when there is no internal heat generation, this will become 0. So that is for all internal point, but for the boundary points, so this is the base of the fin, this is the open end of the fin, and this particular case, this open free end is insulated, so that is why this dt by dx for this is will be equal to 0. And here we have temperature as Tb, which is constant, so this will also be dt by dx for this, and that will also be 0. So now this complete term can be eliminated. So what we get is only equal to minus of xi to xj dnt by dx ka dt by dx into dx. And this term, now I can write this is the left hand side, or this equation, what this equation will take form. This equation will take this form: minus xi xj dnt by dx k into a dt by dx into dx minus, here this nt is to be multiplied by this, so and this I can take these term together and this term with nt together. So what will I get? I will get minus xi to xj nt hpt dx, and this minus this minus and this minus will become plus, so that is why it is plus xi to xj and transpose multiplied by h and p into ta, that is equal to 0. So now this is my equation of interest. So now I have to solve this equation to get finite element finite element formulation for my FEM problem. So that we will discuss in the next slide. So recalling these expressions, that Ti is Ni, Ti, Nj, Tj. If I differentiate this, I get this equation in matrix form. I can write like this, where N is equal to the row vector and this transpose is a column vector. And we can also write this transpose as, I can also write this dn over dx is equal to dni over dx dnj over dx, and differentiation of or derivative of n transpose is dni over dx dnj over dx. So these are our general expressions that we will be using these expressions throughout the FEM formulation of 2D and 3D, whether it is stress analysis problem or field problem, CFD problem, heat transfer problem, any kind of problem. So these relations we should always remember, and not very difficult, because this T is the field variable NITI that we have assumed in beginning, and these are the differentiation, and this is how we can write these in the matrix form. And n is the shape function as far as FEM is concerned, and this is the derivative of the shape function. So these terms will be requiring a lot. So it means when I write this dnt by dx, or the derivative of transpose of shape function, I will write this. When I write here dt by dx, so I have to make use of this equation here. So now I can substitute the values and focus again only the first term of this to write the infinite element form, that is xi to xj minus, and dnt by dx I will write this, so it is dni over dx and dnj over dx multiplied by k into a, that is k into a, and dt by dx I can use this equation, that is dni over dx and dnj over dx multiplied by ti and tj into dx. So this is how I can write this particular expression here. Let me multiply, let me simplify this. I get minus xi xj ka, and then this is to be multiplied, this is rho is to be multiplied by this, so I get this dni over dx multiplied by dni over dx. So the size of this is 2 into 1 and size of this is 1 into 2. So after multiplication I will get 2 into 2 size. So next is to this is to be multiplied by this, so it is dni over dx dnj over dx, and here it is dnj over dx multiplied by dni over dx, and here it is dnj over dx and dnj over dx. So this is what I get after multiplying these two, and k I have taken common here, and this is ti and tj. So this complete expression is known as stiffness matrix. So this is K, and this we can write it as xi to xj ka, and these form, that is dni dx dx and so on, multiplied by ti tj into dx. So this is our first part of this. So this minus sign I am not touching it. So now let us try to analyze the second portion of this equation. And so this I can again substitute, and t I can substitute from here, and t I can substitute from here, that is the t I can write here ni nj, and it is ti tj. So substituting these I can get minus of this nt I can write using this ni and nj, then h, p and t I can write as ni and nj, ti and tj multiplied by dx. So I get this equation as minus integration xi to xj. Here I can write this is 2 into 1 and this is 1 into 2. So I get this as ni into ni, ni, nj, nj, ni and nj, nj multiplied by, let us take this h and p here, multiplied by ti and tj into dx. So this particular matrix is known as convective heat stiffness matrix. So we generally write this with subscript H, representing a convective heat stiffness matrix or thermal stiffness matrix due to convective component. So now I can make use of this. So this is excluding this. This is not the part of this stiffness matrix, and this is also not part of the stiffness matrix. So first two term I can write down minus. If I take minus common, or I can take this these two term on the other side of this. So it is k times for the conductive part of this plus k times the convective part of this, and these both are to be multiplied by this temperature vector, that is T, and this is equal to this third part that we have not simplified. So this will be simplified in our next slide, that is xi xj n transpose H P T A dx. So this is our just one step before our finite element formulation. So we'll be simplifying this and we writing in the case in terms of the finite element formulation. So this equation can be written in the form of xi to xj, and nt can be written in terms of ni, nj, h p ta is constant dx. So this is all about the complete, you can say, representation in the finite element form. This I can write as q. So I can write this complete finite element formulated equation as either this is k and the convective component of k, both are to be multiplied by the nodal variable, that is t, and this is equal to the q. This is how we can represent the finite element form of a FEM problem. So in next class, next session, we will be considering three-dimension heat transfer problem. We will try to develop the general form as we have developed in this case for a 3D. Thank you all the viewers for attending the session. Thanks a lot.